Awesome. Yeah, so today I'm going to talk about our first place solution to the AMO competition. And we'll cover the following topics today. So first I'll introduce our team, then summarize the solution briefly. Then we'll talk about details of our solution. So we'll talk about how we collected the new set of problems, how we generated chain of thought solutions to integrated reasoning solutions. We'll talk about training and inference details, discuss briefly what didn't work, and finally show all the things that we released. So let's go ahead and show the full team. So we had 7 people on the team: Ivan, Dara, another Ivan, Shubham, Christo, Benedict, and myself. We're all from NVIDIA. All right, so here is a summary of our solution. So on the training side, what we did is we collected and processed about 300K mathematical problems from Art of Problem Solving forums. We generated about 2.2 million chain of thought solutions for those problems using DeepSeek R1. We then fine-tuned Quant 2.5 14B on this data to get what we'll call a chain of thought model. Then we prompted this LeMo32B, which is a very lightweight tuned reasoning model, to generate 1.2 million long reasoning solutions that integrate natural reasoning with Python code executions. We then aggressively filtered those solutions down to just 15K high quality samples. And then we fine-tuned our chain of thought model on this data to get the TIR model, to integrate reasoning model. And finally, we merged the two models together to get the final one that we submitted. So these are the details on the training side. And then on the inference side, our system was doing 12 generations in parallel, and we aggregated predictions using majority voting. We used TensorRT-LLM for inference. The inference implementation was fully asynchronous, so different generations didn't need to communicate with each other or wait for each other. So we did it to maximize throughput and be able to cancel generations as needed. We used FP8 quantization, so keeping weights in FP8 and activations in bfloat16. That was about 1.5 times faster than the original. And then we further used the redrafter for speculative decoding, which made the total speed up to be about 2.6 times compared to the original. We implemented a fairly simple time buffer. So if the current problem finished faster than we expect, we allocated more time to be spent on future problems. And we also had 3 different early stopping strategies that we'll cover in details in later slides. Okay, so the final component of our solution was really our code base, which you can see from the name of our team. We used NemoSkills code base from NVIDIA. So that was very important for us to be able to do fast experimentation. So this library lets you orchestrate very complex pipelines for improving language models and do it easily. So there is a simple API to do experiments that combine data generation, training, evaluation. It's very easy to switch from quick experiments that you run on a local machine to large-scale Slurm jobs. It's easy to convert checkpoints to different formats, from Nemo for training to TRT-LLM or Hugging Face for inference. And it also integrates different inference and training libraries in a unified way, so you can easily switch between TRT-LLM, SGLM, VLM, and so on, and different training backends as well. Okay, now let's dive a little bit deeper into the details. So first, let's talk about the problems collection. So as I was mentioning, we use this artofproblemsolving.com forums. So you can see here how one particular discussion looks like. So it starts with a problem definition, and then different people propose solutions. So this one's relatively clean. Sometimes there are multiple problems presented, and people discuss both or many. Sometimes there are no problems at all. Sometimes the solutions are correct. Sometimes people point out mistakes in them. So it does require quite a bit of processing to get clean data out of this raw format. So here is how we structured our pipeline for extracting and processing problems. So we start with raw forum posts, and there are about 600,000 of those. And then each block in this diagram represents a call to an LLM that does some kind of cleaning or processing. So we start with a block that extracts all problems. We then do a series of classifications. Is it a proof question? Is it not proof question? Is it multiple choice? Is it a binary question that's just yes or no answer? Is the question invalid or missing some context? We also try to extract the ground truth answers from the discussion so that we can later use them to filter out incorrect solutions. The final block is the decontamination to make sure that our training set and validation set don't overlap. So here is an example how the prompt looks like for the very first block. So you can see that it's fairly detailed. We give a lot of instructions to the model, and then we show some examples. So this prompt is not complete. There are more examples, and then it ends up with actually giving a particular post to a model and asking it to complete the output field. And each block here is a link. So we published all of the prompts. It's all open source in NemoSkills. Okay. So the only clarification here is that we actually, for the final model that we submitted, we actually did not use these 4 blocks. So the pipeline was relatively simpler. And we'll talk about why that's the case towards the end. So let's now talk about chain of thought solution generation. So we ended up with about 540,000 problems from the problem extraction pipeline. And then we generate a lot of solutions for them using a mix of DeepSeek R1 and QWQ32B. For any solution where we were able to extract the answer, we use it directly to judge whether the solution is correct or not. For any other solutions where we don't know the answer, we just treat majority answer as a ground truth. And for the judge step, we don't just use symbolic comparison. We actually have an LLM call here, and we use Clan 2.5 to be instruct for that. And the model is shown a problem statement and 2 answers, and is asked to compare whether the answers are the same or not in the context of the problem. We do this because in these forums, sometimes the answers are fairly complicated to compare in a rule-based system. So our final data is about 4 million samples. And again, a clarification that while we do have more data for the final model we submitted that took the first place, we actually used quite a bit fewer. So only about 2.2 million solutions, and only from DeepSeek R1 as the teacher. So let's now talk about how we integrated code execution into this long reasoning solutions. So here is an example of a TIR solution where a model reasons in natural language and then at some point decides that it wants to write a Python code to compute something. The output of this Python code is not produced by the model, but instead we extract the code, we execute in an actual Python interpreter, we get the output and we put it back into the prompt, let the model continue. So it turns out that it's actually not that simple to do this. So the reasoning models that we had, R1 and QWQ, are really hard to just prompt into generating such solutions. So we did a lot of tries, we tried to instruct them, show examples and so on. It didn't really work for us. So what we did instead is we took an instruction-tuned model that was trained on a very small reasoning data set. In this case, it was our reproduction of LeMo32B model. And since that model is instruction-tuned and is not overfit to this reasoning long chain of thought solutions, we were actually able to just prompt it to produce solutions that integrate code and natural language. So we used it to generate about 1.2 million solutions, but the problem is that they were actually low quality. And there were mainly 2 problems with them that we tried to address with this filtering step using LLM as a judge. So the first problem was that sometimes the solutions did not add anything new. They just were used to verify existing calculation, which might be fine, but we kind of want code execution to drive towards, to be used outside of just verification. And then the second one, sometimes code execution was done to do something new, but that was fairly simple calculation that is just easier to do in chain of thought. So we designed these two prompts. So these are again just LLM prompts to filter any code block that doesn't contribute significant novelty or is not significant enough on itself. So we filter this 1.2 million solutions down to just 15,000. And you can see that we remove about 99% of the data, but what we end up with is fairly high quality samples that we can then use for training for our final models. And of course, you can do a few more iterations here. So you can now train on these 15K samples, do more generation, do more filtering, repeat this process. So we actually did try that for our best models, but this is not used for the final Kaggle model. So the final Kaggle model is only trained on this 15K high quality samples. So let's now cover the training details. So for the training, we started with Qwen 2.5 14B base model. And we did SFT for about 8 epochs on 2.2 million chain of thought solutions. So for the hyperparameters, we used Adam W optimizer. We used cosine learning rate schedule, fairly big batch size, 16K maximum length. We did leverage advanced parallelization techniques like tensor and context parallel and sequence packing, which helped us to speed up this training quite a bit. They also averaged 4 equally spaced checkpoints to produce the final model, which we find to improve results a little bit. So totally, we used 512 H100 GPUs over 48 hours, so quite a bit of compute. But as you can see on the plot here on the right, we actually could get about 90% of the results with 4 times less than that. And but we really wanted to push the models to the limit, so we did spend all of it to train the best models possible. So this is followed by a lightweight SFT on just 15,000 samples. So this doesn't take almost any compute compared to the first stage. So just do 400 steps with a constant learning rate, not checkpoint averaging, very quick. We use Nemo Aligner backend of NemoSkills for training, and then we merge these two models with just a linear combination of weights. And we use 0.3 weight for the chain of thought model and 0.7 weight for the TIR model. And I should say that when data is more balanced, so when we did generate more TIR data, when it's also millions, you can actually train on all of this together, so you don't need 2 stages. And in fact, the plot on the right shows the joint training when we just use different prompts for chain of thought and TIR models, and that works just as well. All right, so let's now cover the inference details. So for the inference, we used a redrafter technique for speculative decoding. So the idea is fairly simple. Whenever you want to predict the next token, instead of running generations for a big LLM, use a very small RNN head that attached to the last layer, and then you predict 3 tokens using that RNN. And you try to verify them using an LLM doing parallel predictions for all 3 tokens. If the LLM accepts all 3, we take them and move on. If it doesn't accept, we regenerate the first token with an LLM and repeat the process. So this itself gave about 1.5x speed up, which was very nice, and the total acceptance rate was about 65%. So we did train this on the data generated from our final model, so it's important to match the distribution. And we suspect that there are other drafting techniques that might work better, for example, using 2 LLMs, but we did not get it implemented during this competition. So besides the speculative decoding, we also used quantization. We experimented with different options, but the one that showed no decrease in accuracy and gave the best speed was using FP8 activations for the weights and BF16 for the activations. So you can see in this table that it basically has no accuracy degradation compared to the first row, and with redrafter, it's 2.6 times faster. Now for the generations, as I was mentioning, our generation is fully async, so we use in-flight batching And you can see here an example of synchronous generation. So in this case, even though different samples finish at different times, we only get all outputs when the last one finishes. Besides sync generation, you get the outputs as soon as any of them is finished. And you can also integrate this with code execution, in which case, whenever you need to execute code, you stop the generation, you take the Python, run it, and then add it back to the prompt, and you continue the generation. This is, again, fully async, no dependency between different samples. And we use this to be able to cancel different generations to implement our early stopping. So this is combined with a time buffer. For each question, we allocate about 350 seconds. And then there is a variable buffer of 200 seconds that can be added if we finish some problems early. We did implement a different version that's a bit smoother and has less variance depending on the random order of the problems, but it's not used in our final solution. So for early stopping, we use these 3 criteria. The first one is we look at the first 5 generations that are finished. If 4 of the 5 have the same answer, we just take that as an answer and we cancel all the remaining generations. When the first 10 out of 12 are finished, we don't look at the last 2, so we just cancel them to kind of work around edge cases when some generations take a really long time. And of course, if you run out of time in our buffer, we just cancel, whenever that happens and take only the answers that we have. So these are all details of our final submission. And let's not now talk about the things that we tried, but that didn't work. So first, we experimented with different methods to select one solution out of all the generations. And the goal here is to improve upon majority voting. So we tried using different reward models, for example, outcome-based reward models. We tried some heuristics, for example, taking different methods to break ties in majority, like taking the shortest or longest solutions. And we even implemented a novel technique that we call gen select, which the idea here is that you show all of the solutions in the prompt. You ask an LLM to pick one. You can see here that it works substantially better than majority voting, especially at low sample count, which was particularly relevant in Kaggle. So we couldn't do more than 20 generations for sure. And our final method for gen select actually is fairly efficient. So you can use a single model for both generations and selection. And you only need about 10% extra compute compared to majority voting. But still, even with this, we could not really see improvement in scores in the leaderboard, perhaps because the extra time that we need to spend here wasn't, just like the score improvements weren't big enough to justify this extra time that we need to spend. And the other thing we could not do is, as I was mentioning, we actually did have better models than what the model that we eventually submitted trained on more data. Here is the table showing all of the model variations that we trained. So you can see our Kaggle model over here. That's the actual one that we submitted. And you can see that it's substantially worse than the best 14B TIR model that we had. So like 8-point difference here, and also on AMI benchmarks, as even comparable to the 7B model. Why didn't we use the best models? Of course, it's not because we didn't want to. we tried to use them, but ultimately just weren't able to make a high scoring submission. And we think that the likely reason is a combination of these 4 factors. So first, as probably all people know who participate in this competition, there is a fairly high variance in scores. So even if you submit exactly the same notebook, the scores might vary by 2 or 3 points, and sometimes much more. You only have 1 submission per day. So sometimes it's just hard to measure different options on the leaderboard. And we did have our local evaluations, of course, but as you saw, the 7B model worked really well in our local evaluations, but somehow we never saw a high score with it in Kaggle, even though we could do more generations and it was more stable. So we did spend a lot of time focusing on smaller models, in particular 7B, but that might have been a mistake. because maybe our local distribution in evaluation doesn't match what we had in Kaggle, or maybe smaller models just can't solve, a few particular hard problems or something else. But yeah, we did spend quite a bit of time without any benefit here. And because of those two first points, we also didn't really have enough time to address the fact that our latest models turned out that they produce about 10% more tokens on average. So we always controlled for the maximum length, but we only, towards the end of the competition, we noticed that even though the maximum length is the same, but for easy and medium problems, the latest models were just consuming a little bit more tokens, and this accumulated overall, over 5 hours of the submission, and ultimately seemed enough to affect the scores. And we just didn't really allocate ourselves enough time to fix all of this because we maximized the time we spent training the best models, only left about 1 week to submit those final models, and just didn't have time to address these issues. So let's see all the things that we released. So we released the data set that we call open mass reasoning. So it contains all of the data that we generated and collected during this competition. So it includes about 540,000 problems extracted from these forums, 4.3 million long reasoning solutions, 1.7 million TIR solutions, and 560,000 Johnson-like traces. We released a series of open mass nemotron models that are state-of-the-art on mathematical reasoning tasks in their respective model sizes. And this includes our winning model in Kaggle. We also released all the code that's needed to reproduce our results in NemoSkills. So you can go to our documentation, see all of the commands and scripts you need to run to fully repeat what we did. We published a paper with more details. So all of the things are available on these links, fully open sourced, commercially permissive license. Welcome everyone to try and use those. And that's the end of the talk. Happy to answer any questions.